All right. So again, on this slide, UH over element E of X is sum A going from 1 to number of nodes in the element, NA function of position, DAE. Now, because of the way we do this, you are observing that the degrees of freedom and the basis functions which I am drawing are fundamentally associated with nodes, right? Right, and then here also we know that we have a degree of freedom, right, corresponding to each node. We have D1E corresponding to that degree, to that node, and we have D2E. Okay, and for that reason we often also call NAX as being the nodal basis functions. Right, and DAE as being the nodal degrees of freedom. All right. So we've got this far with talking about how we are going to write out this expansion of our finite dimensional trial solution over a single element. We do the same thing also for the weighting function, right? So similarly, for WH function of position, also restricted to element E. Okay, restricted to element E simply because that's where we're defining it. So we do the same thing. WH of E X equals summation A going from 1 to number of nodes in the element, which in this case, because we're looking at the simplest possible finite element formulation, that number of nodes in the element is 2. We have N a function of position. Now, the degrees of freedom for the weighting function will be obviously different from the degrees of freedom for the trial solution, right? These are different functions. So though we're using the same basis functions for the weighting function and the trial solution, we have to use different degrees of freedom. If not, they would be exactly the same function, right? So we have C, A, E. Okay, where in this case, again, this is the degree of freedom, DOF for short, of the weighting function. All right. Okay, let me see. There are many things to be said about this, but first of all, this is our most elementary sort of approach to writing out a Galerkin weak form. When we have the same sort of basis function for the weighting function as well as for the trial solution, right? This is called a Bubnov-Galerkin method. Okay, and what this means is that same basis function for UH of E and WH of E. There are other more advanced finite element methods that, for good reason, because of certain things to do with the mathematics of the particular equations being solved, do not use the same basis functions for the trial solution and the weighting function. And they are called Petrov-Galerkin, when we won't get to them in this series of lectures. Okay, so, all right, let's move on here. Now you will note that all I've done so far is to sketch what these functions are going to be. I've called them linear functions, and so you can imagine what they are. You could very well construct them in terms of position over the, in terms of the x coordinate over the element. But it turns out that we can do better. We can do something much more systematic. Okay, and here's how we do it. We first take this approach where we say that this element of interest, which has coordinates xe and xe plus 1, we regard this as being the physical representation of the element, right? Or this is the element in the physical domain. Okay, so we call this the physical domain. In order to construct our basis functions, we always think of any element, of an arbitrary element, as being constructed from a mapping, right, from a different domain. And in this domain, the element is going to look similar, okay, except that it is, I'm not going to use x for position along this, right? Whereas I have x for position in the physical domain, I'm not going to use x in this domain. In this domain, I'm going to use xi, right, as a coordinate. And this point here, the node on the right is xi equals 1. The node on the left is xi equals minus 1. And the midpoint is xi equals 0. It's important to note that I have not introduced 3 nodes. The nodes that I think of are still xi equals minus 1 and xi equals 1. Okay, I've just marked the midpoint. The midpoint is not a node. Okay, so these are the nodes, right, in this representation. Now this is called various things. Some people may call it the mathematical domain. I call it the bi-unit domain. Bi-unit because I'm saying that the length of my element in this domain is, it goes from minus 1 to 1. It's 2, right? So it's 2 times 1. So it's a bi-unit domain. Now, we always think of our actual physical element as being constructed from a mapping, as a mapping from our bi-unit domain. Okay? Why do we do this? We do this because it becomes very convenient to define things like our basis functions and later on to carry out integrations if we have this idea of the bi-unit domain. Okay? And in fact, here's what we will do. Our basis functions, n1 of x, we will write as n1 of x, but really x, remembering that x is a mapping from this bi-unit domain, right? X is a function of xi. And likewise, n2 of x equals n2 x mapped from the domain, from the bi-unit domain. Okay? Now, strictly speaking, there is an abuse of notation going on here because I cannot have a function parameterized in terms of x and then use the same symbol for the function when parameterized in terms of xi. Okay? But I will nevertheless follow that abuse of notation because otherwise our notation just gets much too unwieldy. Okay? All right. So now that we are in this bi-unit domain, it becomes very convenient to write out our basis functions. Here they are. n1 of xi equals 1 minus C divided by 2, and N2 of C equals 1 plus C divided by 2. Okay, completely clear what's going on here. We have C equals minus 1, C equals 1, that is our point C equals 0. If you just evaluate 1 minus C over 2, what you will observe is that at C equals minus 1, it takes on the value 1. Okay, so this is the value 1. Okay, and it goes to 0 at C equals 1. Okay, this is our function N1. Sorry. That is N1. For N2, let me try and use the ability here to go to a different color. For N2, I have that. Okay. That is N2. That is again the point 1, and you observe that when we're at C equals minus 1, N2 drops to 0. Okay, so let me just write those facts here. Okay, what we observe is that N1 at C equals minus 1 equals 1, N1 at C equals 1 is 0, N2 at C equals minus 1 is equal to 0, and N2 at C equals 1 is 1. Okay? Now, if we write these points C equals minus 1 and C equals 1 as, let me call this point C1 and this point is C2. Okay? Just corresponding to the idea that the node on the left in this bi-unit domain is node 1 for the element, and the node on the right in the bi-unit domain, this one, is node 2. Okay? What that then lets me say is that NA, okay, whichever shape function, whichever basis function you want to use, by the way, basis functions are often called shape functions. Okay, I just prefer the term basis function. Okay, if you take basis function A and you evaluate it at CB, this is the Kronecker delta. Okay, and you know what the Kronecker delta does, right? Kronecker delta is equal to 1 if A equals B, and it's equal to 0 if A is not equal to B. Okay? The basis functions that we have described here have the so-called Kronecker delta property. All right. Okay, so we've got as far as describing our simplest, indeed our simplest basis functions for this finite element formulation, the simplest of finite element formulations. We will continue with this, but this is also a good place to end this segment.